go. Okay, so first thing we're going to talk about the difference of two squares. It's not particularly amazing, but it's nice if you could recognize it. There are some situations where it does crop up for the quote-unquote more difficult problems. So let's, of course, see the construction behind such situations. So a difference of two squares is exactly what it is written. The name of the situation is pretty informative. So a square is anything that you have an exponent that's an even exponent, and then the typically the numbers are perfectly squarable. So for example, you'd have like a 25, that's going to be a square because it's 5 squared. Or you have 9 is just 3 squared. And then you're going to have like 100. Generally, you have very nice numbers. Learn to recognize these ones, of course. Let me just start listing a few of them. I'm not going to particularly emphasize these, but it's nice, you know. Put them off to the side right here. Again, these are the most common ones. We have 1 squared is 1, 2 squared is 4, we have 3 is 9, and we have 16. There's no need to memorize these, but of course, it's always nice if you do. So you're going to see these very common numbers. You might see a few larger numbers, but for the most part, you're going to see stuff like this. And then for your variables or unknowns, you're going to have like x squared, most common one. You have y squared. Perfect squares right here, very simple. Of course, you could have higher numbers up. You could have x power 6, x power 8, x power 400, for example. And then you might see some other different letters. You might see like A's, you might see B's, but that doesn't matter. Learn to recognize the form. So a difference of two squares. Let's look at the grammar of that. So first word is difference. And then you have the prepositional word of, and then two squares. So when you translate such a thing, typically in math phrases, when you have of, especially, and then this prepositional, you carry it all the way to the noun right here. You have squares, so it's a difference of two squares, which means that you're going to have square number 1, and then there's going to be square number 2, and then you have the keyword difference of. So just subtracting those. Let me color this a little better. Difference of, there it is. So difference of two squares, very straightforward translation. So for a square, as an example, you can get like 25x squared. And then second squared could be something like 9. So learn to recognize the situation. It's pretty nice. It's kind of a niche situation. It does crop up quite... Well, actually, let me retract that. I wouldn't say it's a niche situation, but there are a lot of difference of two squares embedded throughout different problems. You're going to have the introductory factoring problems, and then you're going to have fractions with rational, what are those called? Rational expressions on them, and then you have to simplify some sort of fraction. You might see them in calculus when you are trying to take limits. They crop up. They do crop up. So it's not super niche. The later ones after the difference of two squares are a little more niche, but continue on with this one again. Recognize the two forms. So this is perfect square number 1. This is perfect square number 2. This is a difference between those two squares. And then how do we factorize those? It's fairly straightforward, but let's look at the mechanics first. So suppose we have a fully factored form, and then you're going to see where the numbers have come from. So let's say this is going to be 2x, and then this is going to be 2x, and then this is going to be minus 3, and then this is going to be plus 3. So just take a look at what's going to happen after you distribute this 2 by 2 situation. So if you multiply those two out following, the 4-letter F word distribution, we have 2x times 2x, which yields 4x squared. And then for second term times first term, we're going to get negative 6x. And then we have first term times second term, thus yielding, let me put it right here, yielding a positive 6x. Interesting. And then lastly, we have the negative 3 times the positive 3, which gives us negative 9. So again, just be aware of things, where things are coming from. So the 2x here times the 2x here yields the 4x squared, and then the negative 3 times the positive 3 gets the constant negative 9. And then, of course, we have the two middle terms. Product of the two middle terms, we're gonna put it right here, the negative 6x, and then the positive 6x from those two. And you notice something, if you summate those two, equal and opposite signages, so equal magnitude, opposite signs, and then this is just exponent 1, so they're like terms. So when you summate those, you're going to get 0x. And this is particularly important. So this is 0x is gone. And we're going to just copy paste the remaining two terms. So we still have the 4x squared, and then we still have the minus 9. This is 0x. You can put plus or minus. It doesn't matter, because once you think about it, you don't need to write this after you get it 0. So full cleanup, we're going to get 4x squared minus 9. So there we go. That's how we get the difference of two squares. This is going forwards from fully factored form into the difference of two squares situation. Again, learn to recognize this. It's basically the vast majority of these difference of two squares are just going to be basic exponent 2 type of quadratic. They could be higher degrees, as mentioned before, but for the most part, most of those you'll see will be in quadratic form. It's just that the middle term is gone because it has a 0 coefficient in the front. So difference of two squares. So that's going forwards from the distribution. So if we were to go backwards, if we were to factorize this one, like how do we factorize such a situation? Well, you could see that the 0 term has disappeared, so you could always manually insert the 0 back, just to make the process more streamlined, or more uniform, I mean. So when we're factoring such a thing, you typically, for quadratics, you have 3 terms rather than just having 2 terms, right? So let me write a problem real quick. So if you have something like x squared minus 3x, and then we have minus 4, this is a classic nice situation with the 1 front. So how do we factorize this one? Again, just because this is coefficient 1, you ask yourself, what are the factors of 4 that could potentially produce this negative 3 if you use distributive property? So factors of 4, we have 2 and 2. We also have 4 and 1. Which of those factorization schemes can possibly summate to be negative 3? Well, it's got to be this one. Not the 2 and the 2. So we write our skeletal factorization. We have the x squared production from this x times this x. Pretty easy. And then, of course, our hypothesis is for here. Let me put the 4 here. 4 there, and then the 1 right there, because, again, 4 times 1 gets us 4. But we have a negative sign and another negative sign. So this tells us that the larger of the two signs, the larger of the two terms is going to be negative. So this one is going to give us 4x, and this one gives us positive x. So therefore, the negative belongs on the 4, and then the positive belongs on the 1. This is just review, one at a time. Hold on, there's like a weird scratching sound. Okay, like a piece of paper that's like rubbing up against the keyboard, but it's gone now. Okay, so there it is. So this is fully factored form. Again, all these numbers have come from somewhere. These numbers have come from somewhere, and that's how we generated this fully factored form. It's going to be the same thing for a difference of two squares. So if you don't like that it only has two terms, you could always manually insert the third term yourself. So here's what I mean. We have the 4x squared, and then the middle term, you just put plus 0x, as mentioned before. Or you could put minus 0x. Quite frankly, it doesn't matter. I just like positives. So plus 0x in the middle, and then we have 9. Standard question is what we've always asked before. So the question is, how do you produce this 0x using the factor plays between the factors of 4 and the factors of negative 9. So let me list the factors of 4 yet again. 2, 2, 4, 1, and then the factors of 9. 9, 1, 3, and then 3. So which of those combos can potentially yield a positive 0? Well, it's very nice, because you want the two products to be equal magnitudes. So you're going to pick the same numbers. So you want the 2 here. We're not going to pick the 4 and a 1 and then the 9 and a 1, because those ones produce different magnitudes. Because, for example, 4 times 1, if you think this is a 4x here, for example, and then you think it's a 1 right here, and then this is going to be the 1x right here, and then the 9 goes here, you can see that the magnitudes you produce from the distribution are not the same magnitude. So there's no way you can cancel them to make 0 with any scheme of pluses or minuses. So for the special situation of producing the 0 middle term, you need to pick the same numbers. So what I mean is 2, 2, and then 3, and then 3. So using that to populate our fully factored form, those 2's belong in front of the x's. Again, this is just review. And then we have the 3's here, the constants. So 3, 3. The two signs are different, and it doesn't matter which one's the larger or the smaller, because they both should be equal sized. So check it out. So if you distribute these two, you're going to produce negative 6x, and then if you distribute those two, you're going to get positive 6x. And as calculated, we see that the negative 6x plus the positive 6x will produce 0x that we desire in the middle, which you don't have to write, so you can simplify it back to this. All right. So those ones, again, the 4x squared, that's comes from the first term times first term, so that's good. And then the two middle terms have canceled out, and then the last term times the last term, negative times positive, gives us negative, and then 3 times 3 gives us 9. So again, these two terms cancel each other out because they are equal magnitude, equal size, and they're also opposite signs. Equal, but opposite signs. Okay, so that's the conceptualization behind what we're doing when we're trying to factor the difference of two squares. You just want to produce a middle term of 0. So if we're doing this one in particular, if we were to factorize this one, you can imagine there is a 0x in the middle. You don't have to do this, but if you're starting off and it feels kind of weird, you can always write this out yourself. And then we have a minus 9 there. So this problem, you can think about it in your head as 25x squared plus 0x minus 9. So factorizing this one, thinking about the factors of 25, we have 25 and 1, 5 and 5. And then the factors of the negative 9, 9 and 1, 3 and then 3. We want to produce a 0, so we know that we have to pick the same numbers for both parentheticals. So again, these 5, we're going to pick the two 5's here to factorize this 25x into 5x here and then 5x there. And we're going to pick these two 3's, 3 here and then a 3 there, because we know when we use distributive property, these ones will multiply to become 15x, which is equal magnitude to this one times that one, which is also 15x. But we just need differing signs. This negative tells us the two signs are different. So one of them has to be negative and the other one has to be positive. It doesn't matter which order because they're the same magnitudes. Same magnitudes. So this one yields positive 15 and this one yields negative 15. So when you sum it, you produce no term in the middle because it's 0x. So perfect. Do you have to go through this entire process? No. Once you get enough practice, you just know to take the square root of that one will get you the 5. Square root of that will get you the 3. Those ones must be the correct situation. Otherwise, the two middle terms will not cancel. So yeah, this is just the difference of two squares. It's pretty nice. Learn to recognize them. Let me give some fairly straightforward problems. We have x squared minus 9. Very easy problem. We have a 1 coefficient in the front. What are the factors of 1? 1 and 1. So when you think about that, you were populating the fully factored form. So again, how do we produce this positive 1x squared? It must be positive 1x times positive 1x. How do we produce this negative 9? Well, you're not going to put 9 in 1, because this one, if you distribute, gets you 9x. That one, if you distribute, gets you 1x. And if you put, no matter what plus or minus you put in between those, you will never obliterate the middle term. So this is incorrect. So once again, once you learn the algorithm, once you recognize that this is a difference of two squares, you just take the square root of 9, which is just 3. And then to produce 9, this other one has to be 3. And once you populate that like this, you recognize that these two will produce 3x, which is the same magnitude as this one times that one, which is also 3x. Just make sure the two signs are different. So minus plus. And once you check up the signages, you recognize that the two summate to become 0x. Perfect. Another situation, we have 25 x to the power of 4, and this is going to be minus 100 y squared, and then z power of 4. Learn to recognize the difference of two squares. 25 is a perfect square. X power 4 is a perfect square. 100 is perfect. This is even exponent, so that's perfect. Even exponent, so that's perfect square. There's a difference between perfect square number 1 and then perfect square number 2. So we can factorize this as a difference of two squares. So speeding up just a little bit, square root of 25 is just 5 and 5. Square root of this one, if you recall, square root, we're just applying the 1/2 exponent. So you can distribute the exponent following exponential rules, and then you get x power 2. Be careful of pluses or minuses, but since we are transitioning from even powered exponent to also even, you don't need to put absolute values. So no weird plus or minus shenanigans to worry about for the situation. So square root of x power 4 is just going to be x squared here, and then x squared there. So just double check. If you distribute those two, do we produce this thing in the beginning? Let me get rid of the circle real quick. So again, this is going to be x squared, and this is going to be x squared. So if we distribute those, will we get back to the 25x squared? Yes, we do, because 5 times 5 is 25. X squared times x squared. Recall your exponential rules, same base, same base. All you need to do is summate the two exponents. It's part 4, so that checks out. X power 4, so that's a perfect match with this one. Good to go. And again, because we recognize this is a difference of two square scenario, what's the square root of 100? It's just going to be 10. And the 10 here, what's the square root of y squared? This is the one that gets kind of annoying, because the square root of y squared is going to be y power 1, but because you are taking the square root of an even powered exponent, if it transitions to become odd exponent, you have to put absolute value. Otherwise, things get kind of screwy. And again, that's just a review from a while back. So once you write that down, make sure you put absolute value y and then absolute value y. Otherwise, you'll be losing a potential answer. All right. Then of course, we have here the z power 4. That's going to be straightforward. It's going to be the same thing as this x power 4. So what's the square root of z power 4? It's just half the exponent is 2. So z power 2 and then z power 2. So that's how we begin to populate the two factors. There's a negative sign between term perfect square number 1 and perfect square number 2. You know, that's just the form of the difference of two squares. So the two signs must be different. So this, I'm going to arbitrarily put it as positive, and then this one arbitrarily as negative. Okay. Quick check. Make sure the product of these two terms must be the same magnitude as the product of those two terms. So let's check it out real quick. So if you distribute, first things first, we have a negative, and then 10 times the 5 gives us 50. And all these letters, they're not combinable. So we'll leave it like this. That's this one times this one. And then the first term times the second term. What do we get from that? 5 times, well, first the signages we have positive, and then the 5 times the 10 is 50. X squared times those other two unknowns, so no combining. We'll get something like this. So this is x squared times absolute value of y times z squared, which is the same thing as this one. Perfect. They're same type of terms, so we can combine those two by adding up the coefficients. We're going to get 0. You know, that's pretty much what we expected. So the two middle terms will have canceled, so this is fully factored form for this nonsense right there. So, good to go. As you see, not too bad. Do you always have to have a perfect square? No. So if you have, look at these numbers right here, right? If you see these numbers, the problem maker was being nice, giving you perfect squares, but will you always get perfect squares? So for example, can you get something funky like a 20? Yes. Depending on how annoying someone wants to make a problem. So you could have 20x power 2, for example, and then you can have minus the 9. Let's keep it simple. Suppose you have something like this. Can you factorize this? Yes, you can. It's just that the coefficient for one of your factors will be irrational, but you can still write it. We're going to ask ourselves the same question, same template setup. It's going to be factor number 1 times factor number 2. What's the square root of this 20? Well, that one's a little funkier. You can just cheat and just say square root of 20 times square root of 20. Because if you recall, if you have the square root of a number times also a square root, the square roots will basically add up to become positive 1 exponent. So, and then the number remains on the bottom. So that's just the algorithm. Let me just explain that using fractional exponents real quick. So don't forget, if you have a radical notation, that just means an exponential, that just means a fractional exponent. What that means is that we can translate this one into 20 to the power of 1/2, and then the second one times 20 to the power of 1/2. Same base here as the base there, so you could just simply summate the two exponents, thereby getting 20 to the power of 2/2. That is simply 2 to the power of 1. Anything to the power of 1, that's just itself. This is really bothersome. Why is this here? Let me try to... Wait, there you go. Okay. This program is kind of buggy. This is a very old program. Anyway, so that's the reason why you have rad 20 times rad 20 gives us just plain old 20. It's for this precise reason, but a lot of people forget that you could just change this one into fractional exponents. Or they take it for granted, I should say. Alright. That's just a long, convoluted side tangent just to, well, not convoluted. This is a side tangent to just explain why this one times this one gets back to 20. Okay, and then you take the square root of x squared. It's just going to be x here and x there. Technically, when you take the square root, you're supposed to put absolute value. Maybe it doesn't really matter for the situation. maybe. I'm going to put it just to be safe. So let's put absolute value here and an absolute value there. Then we have square root of 9 is just going to be 3 and then the 3. The negative between term number 1 and term number 2 tells us that the two signs must be different. So minus and positive. I think we could drop the absolute values. Because if this is a negative value and this is a negative value, when you distribute, it's going to become back to positive. If this is positive times positive, then it's still going to be positive. So I think, yeah, I don't think you typically need to write the absolute values. Yeah. Because this term here and this term, they're going to interplay with each other. Versus if you just have a problem like this, and then you solve for x by taking the square root of both sides. This is the one where you're transitioning from even powered exponent into odd power exponent, so you have to put plus or minus 3. Whereas factoring like this, the two signs will cancel regardless, because you have x, the same x here as the same x there, I think. Yeah, so I don't need to put absolute values. So let's drop those. And let's also simplify this 20. So recall that 20 is just going to be 4 times 5. The reason why I factored the 20 like that is because the 4 is a perfect square. We can simplify this. Don't forget, the radical just takes half of the exponent. So we can take half of this exponent to quote-unquote bring out the base 2. Then the 5 here has exponent 1. That's not a 1 divided by 2 is not a whole number, so we leave the 5 inside the fractional. Like that. Copy paste the x without absolute value signs. Minus 3. This is factor number 1. And then factor number 2, we're going to do the exact same thing to this root 20. It's going to be 2 root 5. Copy paste the x plus 3. Close parentheses correctly, and this is fully factored form for the start of the problem right here. So again, this 20 here is not a perfect square, but you can still take the square root. You're just going to have irrational coefficients, which you may or may not get, depending on how annoying the problem maker wishes to be. Alright, so that's just a difference of two squares. It's pretty nice. It's not too difficult, in my opinion. It does get a little bit more annoying when you see a bunch of letters like this one, but it's not too bad. And again, I think you can just drop the absolute value. So that is the difference of two squares. It's nice if you can memorize perfect squares. So I don't think people go beyond 169 or 196, I believe. The majority. So let me just list a few more of these. 49 is going to be one of your favorite ones to recognize when you see difference of two square scenarios. 64, it's pretty nice. 81, 100, 121, and then you see the other ones like 169. No, 144. That's 12 times 12. You're going to see 169. I think that's 13 squared. Yeah, the 3 times the 3 is 9, yes. And then you see the 196. Well, the 14, and then maybe 225. Again, most problems don't really go that far. Most of them stop at... You're not going to get any perfect squares beyond 15 for the most part, except maybe 625. It's 25 squared. So again, these are the most common ones. Learn to recognize those. Once you see it, it's like, oh, that's going to be a difference of two perfect squares. But they don't have to be perfect squares. You can have irrational coefficients as well. Okay. It's going to be a little shorter today because I have things to do at around 7 o'clock in like an hour. So this is a general overview of the concepts behind, or I guess not really so much the concepts as it's just the mechanics of the difference of two squares and then the difference of the sum difference of two cubes, and then factoring by grouping. So let's talk about the next related situation. That's fairly close to a difference of two squares. It's going to be the difference of two cubes. So by cubes, we're going to start with the same base numbers. So if you have one cube, that's just going to be 1, and then if you have 2 cubed, that's going to be 8. You should memorize these ones, but it's not super important, I would say. 3 squared is 27, 4 squared is 64, 5 squared is 125, 6 squared is fairly, or what did I say, squared, cubed, but then 6 cubed is going to be 36 times 6. What is that? 21/6. Okay, so you're not going to see these numbers. They're not going to go beyond 6 very often, honestly, but they might. No guarantees. And very similarly, just make sure you recognize the grammar difference of 2 cubes. See the prepositional word again. So there's going to be a parenthetical difference of 2 cubes. So similarly to the difference of 2 squares, there's going to be cube number 1, and then there's going to be cube number 2. So there's cube number 1, and then there's going to be cube number 2. Difference of, so it's minus. So thus, the first one is going to be a perfect cube, like x cubed. Easy example. And then the second cube might be something like 8. So again, that is the difference of, parenthetical, 2 cubes. Cube number 1 and then cube number 2. So learn to recognize these ones. The factoring scheme for this one is a little more complicated than the difference of 2 squares. Again, it's easy to trace where the coefficients have come from if you're working with quadratics. But this is polynomial of degree 3 or greater, so the tracing is a little more annoying, but we do have some ways to go about doing this. Alright, we're actually going to start with the synthetic division first, actually. So this one, you could use long division, but long division is inefficient. So rather than long division, you do the shortcut, the streamlined version of long division, which is just synthetic division. So this is a review from last stream most directly, or math at least. You got to make sure you account for all terms because your synthetic division is a very mechanical algorithmic process. You have to have all players present. Here's what I mean. You can't just say, oh, I have coefficient 1 and number -8, and then therefore I'm going to put 1 here and -8 there, and I'm going to do my synthetic division. You cannot do it like that. Because again, the synthetic division is very mechanical, and because it's very mechanical, it's like one of those old school machines. You have to feed every single part, otherwise the machine's going to fumble the situation. So again, what I mean by that is there are those invisible terms. Make sure you account for all degrees. They must be present. This is degree 3, so yes, we have 1x cubed. That's the highest degree that we can see. Then you have to account for the x degree 2, which is not present originally. It's going to be plus 0x squared. As long as you put a 0, you're not changing the problem. But we're just, again, we're accounting for the invisible terms. So the 0 here has to be fed into your synthetic division machine. So it's going to be 1, 0. Same thing is true for the x degree 1. It just has coefficient 0. Again, x degree 1, and then this one is technically x degree 0. So now all terms, including invisible terms, are accounted for. So we're going to use that to populate the synthetic division algorithm hockey stick thing. So it's going to be -8. Okay, so what are we testing as a factor? Well, it's just going to be, honestly, just a cubic root of this 8. Because remember, we're dealing with the difference of 2 cubes. So this is going to be a cubic. So the cubic root of this 8 is just going to be what? 8 factorizes into 2 times 2 times 2, which is cube. Hence, that's why it's called a cubic. So if you apply the cubic root, which is 1/3, 1/3 distributed to 3 gives us 2 power 3 over 3, which is just 2 power 1. So why are we saying this? Why are we taking the cubic root of this? Because that is what you're going to use for this one. Okay? So as the 0 candidate for the synthetic division algorithm, we're going to put a 2 right here. So following the procedures of the synthetic division, you just drop this down. Product, summate, product, summate, and then lastly product, and then last summation, which is 0. Very easy, very straightforward. You don't have to memorize anything. This is nothing new. You just use your standard synthetic division algorithm, and the candidate is always 100% positive 2, because if this is a positive 2 cubed, you're going to get positive 8, and then positive 8 minus 8 gets you a 0. That's why this is called the 0 candidate, and that's why we're not picking negative 2, for example. So there's no confusion. You only have one real candidate to test, unlike the other annoying polynomial factorization problems you have to do. That one is like a lot of guess and check, depending on how annoying the coefficients are. But these are very simple coefficients. It's just 8 and 1. So that's nice. So as you see, it's a little mechanically similar to the difference of 2 squares. Like again, you have x squared minus 4. For that one, you figure out the factors of 4. But they're going to be the same factors because it has to be 2 and 2 in order to cancel out. So it must be in order for the 2 middle terms to cancel out. So x minus 2 times x plus 2, because again, this product is going to be positive 2x, and that product will be negative 2x, resulting in cancellation of the middle term, which is perfect. And this was the same idea. You know, you want this 1 here, you want to produce this negative 8, so that's why we are testing out this particular 0 candidate for the synthetic division factorization. Alright, so that's the similarities between those two. But now, talking about the difference, what does this mean again? This 2 here is a 0. Quote unquote 0. And if you recall from previous time, zeros are almost synonymous with factors. You can translate the, if you're given a 0 of a polynomial, you can just transform that into a factor. So if 2 is a 0 of x cubed minus 8, then x minus 2 is a factor of x cubed minus 8. So almost synonyms. If you're given a factor, you could transform it into a 0. If you're given a 0, you could transform it into a factor. Okay? Just make sure this is a positive 2 minus 2 gives us 0. Okay, so that's one factor of our x cubed minus 8, but what's the leftover that we have? Don't forget, it's right there. So we divided our x cubed minus 8 technically by x minus 2, so we should have degree 2 left over plus 2x plus 4. If you don't see a negative sign, it's positive. So this is the quotient that results from dividing this one by that one. So the quotient should go right here. So let's write that down. Again, this is just technically review. We have x squared plus 2x and then plus 4. So it's a little bit more, it's a little bit extra compared to the difference of 2 squares factorization. This is like super easy, but then this one looks a little funkier right here. There is an algorithm to do this, to jump straight from here to here, and you can memorize it if you wish, but it's in all honesty, it's not that important. Knowing the syntactic division is a little more useful if you proceed down that pathway, but I'll show you the shortcut regardless. So you see how that's an x cubed? What's the cubic root of x cubed? It's just x power 1. And you see how this is a negative 8. What's the cubic root of negative 8? It's negative 2. There. And this is how the rest of the algorithm proceeds. Again, we already explained why it, or rather we showed a different mechanic, but now, what is this one squared? It's that. What is negative 2 squared? It's the last term. And then to produce this middle term, all you have to do is take this x times the 2, ignoring the sign. So just x times the 2, ignoring the sign, to get this one. 2x. And then you have to alternate the signs. That's if you want to memorize the algorithm. Again, it's not particularly important. It's not super useful. It'll save you maybe, I don't know, 4 seconds. You don't have to do syntactic division for 4 seconds. That's like wonderful time saved, right? So in the grand scheme of things, it's fairly insignificant, relatively speaking. I mean, syntactic division is kind of insignificant as well. It's just an algorithm that works for division by singular exponent, by exponent ones. Not tremendously useful in the grand scheme of things, but this is even less useful. It does crop up when you're doing calculus, for example, and then you're asked to find limits, and then you might have a difference of 2 squares in your rational expression, and then if you've forgotten how to factor it, then you just use long division. Again, not a particularly big deal. There it is. All right, let's do some difference of 2 cubes. Again, you'll see it's not too bad. So we're going to have perfect cube number 1, so it's going to be 27x to the power of 6. You know, this, what's the cubic root of that? It's 3. What's the cubic root of that? It's x squared. So 6 divided by 3 is 2. So that is perfect cube number 1, the difference between cube number 1 and then we're going to have cube number 2. So 125 and then y exponent 30, just to be funny, right? And then we'll throw in a z here as well. You know, it doesn't matter how many letters you put as long as they're all perfectly divisible, as long as the exponents are perfectly divisible by 3. So 121. No, that's not it. 120. Yes. Now let's make it 120 with 3, just to be funny. Because 1 plus 2 is 3, and then 3 plus 3 is 6. 6 is divisible by 3, so 123 must be divisible by 3 using that little division trick. Alright, so again, difference between cube number 1 and then cube number 2. I'm going to do the algorithm and then I'm going to do the long division just to show that it's gonna work out. Wait a minute. No, let me just do the algorithm first. So this one right here, again, what's the cubic root of this 27? It's just 3. Because 3 times 3 times 3 is 27. Exponent divided by 3, just to take the cubic root, is 2. So we're finished with the 27 and then the x power 6. Minus. What's the cubic root of 125? It's just going to be 5. Cubic root of y power 30, take the 30, divide that exponent by 3, is 10. Lastly, take the cubic root of z to the power of 123. So divide by 3 is 41. So that's just the beginning. We have the rest of this quotient to deal with. Like I said, to figure out this one, all you have to do is take this 3x squared and then you square it. So what is 3x squared squared? So first, square the 3. Second, square the x squared times 2 to the exponent. Finish with that one. how do we get this old middle term right here? It's just going to be this one here times this one here, and then you flip the sign. So first you flip the sign, positive, and then you do the 3 times the 5, which is 15. X here, there aren't any x's there, so don't worry about that one. Copy paste the rest of these factors. There we go. And of course the last term inside this quotient box, just take that one and you square it. What's this one squared? It's positive 25. Square that is just y power 20. And lastly, square that is just z to the power of 82. And you're basically done with the problem. That's full factorization of a difference of 2 cubes. There it is. Again, what algorithm? I was following this particular algorithm that you could easily derive by doing a much simpler problem. So if you ever forget it, just derive it first. And then once you derive it, you can apply it to your more complicated looking scenario. And the derivation takes less than 10 seconds, I would say. In fact, give yourself easier numbers, right? So if you're trying to derive what's the algorithm, you could just start with x cubed minus 1. Well, maybe minus 1 isn't that useful. Let's do minus 8. So again, this one is a difference of 2 cubes. You can use your synthetic division. What's the cube root of 8? What's the cube root of negative 8? It's just negative 2, but you pick the positive 2 because positive 2 cubed gives us positive 8. And positive 8 minus 8 gives us 0. So 2 has to be a 0 of this polynomial. Alright. What are the coefficients? Don't forget, there's a 1 in front, and then there's the 2 middle terms, 0x squared, and then also 0x 1. So 0, 0, and then negative 8. That's your last term. Following the algorithm, summate, product, summate, product, summate, product. Of course, we get 0 as expected. And all those numbers here, remember these mean something. This is the number in front of the x squared because we started off with a cubic. We're dividing by technically x minus 2. So the exponent gets reduced by 1. Downtick. So this one times that one gets us back to this one. So again, this was a 0. You could transform into a factor. Multiply by the leftover quotient. So using this, you can figure out the algorithm for factorizing a difference of 2 cubes. A cube root of that is that. Cube root of that is that. This one squared is that one. That one squared is that one. And then this times this one, flip the sign, gets you to this one. That's the algorithm. I think I said that I would do synthetic division for this one, but it's not a nice scenario exactly. So we're gonna just leave it as such. So follow the algorithm. I'm sorry, that's just the way it be sometimes. So that's the difference of 2 cubes. Difference. But what if you have the sum of 2 cubes? So cross that out. It's not going to be sum. Summation. Well, for the most part, it's going to be the same thing. It's pretty nice, actually. So maybe if you're taking a test or something, and then maybe for some reason you've forgotten the sum of 2 cubes algorithm, it's going to be very similar to the difference of 2 cubes algorithm. Very similar. Promise. So, suppose we have 27 x power 3 and then minus perfect cube number 2 is 125. But this is a sum, so it's going to be plus. This is perfect cube number 1, and then that is perfect cube number 2. It's a sum of 2 perfect cubes. So you ask yourself, well, what's the cubic root of those two, right? So cubic root of the 27 is just going to be 3. Cubic root of this one, divided by 3. That's a cubic root. First term. Second term, because it's a positive 125, cubic root of 125 is positive 5. So cubic root, and then cubic root. We know that there's going to be a larger chunk inside here. 3 terms. Term number 1, term number 2, and then term number 3. How do we get those 3 terms? Square this one to get the first term. Then square this one to get the last term. So if you're squaring a positive 5, it's still positive. And then the middle term is the one that could potentially get messed up, but just follow the algorithm. First term times second term. Flip the sign. So 3 times positive 3 times positive 5 gives us positive 15, but you flip the sign, so it's negative 15. Well, then x here has nothing, no other x's to multiply 2. Copy paste. And that's it. That's the algorithm. Again, if you ever forget, you can do the very easy situation of something like x cubed plus 1, for example, right? Or, you know, 1 isn't very informative. I'll pick a better, let's go back to 8. Or even 125. Yeah. So this is a perfect cube number 1. And then this is perfect cube number 2. It's a summation between those two in order to derive the situation, derive this algorithm. Just remember, you got to use synthetic division. You have term number 1 with a coefficient of 1. And then you have term number, this is not term number 2, technically. There are 2 invisible terms. Again, there's going to be 0x squared, and then there's going to be 0x power 1. We have to consider these in order to fully populate your synthetic division machine, because your machine is not that good, so you have to feed it all the relevant layers. There it is. So again, changing it from the given problem, remembering that there are invisible terms in the middle, and now we've populated the synthetic division machine. What's the 0 we're testing? What's the cubic root of 125? It's going to be 5. But this is your 0 candidate. So we have to produce a negative if we cube it. Otherwise, it won't cancel with this 125 to produce 0. Then this would not be a 0. So, again, if we leave our candidate as positive 5 and then you square it just to test it, you're going to get positive 125. Positive 125 plus 125 does not produce 0. So this is technically not the 0. It needs to be negative 5. So you need negative in front of that one. So see what happens if you cube that. If you cube it, you get negative 125. And now the sum of those two gets you 0. That's what you want. So we know negative 5 is a 0. Which might feel superfluous that we're finishing this synthetic division. But remember, we want to get the quotient so we get the remaining part, the rest of the function. We don't care that we get to 0. Well, we do care. But we're picking this negative 5 because we want to generate this portion here to figure out the rest of the factor that multiplies to this one to produce the original situation. Okay. So let's do that. Drop the 1, product, summation, product. Negative times negative gives us positive, summate, product. Negative times positive, of course, is what we calculated. Gives us negative what? 125. This is what we wanted, 0. This is what we wanted to produce, but this is the thing that we actually cared about. This is the coefficient for x squared, coefficient x power 1, and then this is just a constant. So that's the quotient if we divide the original problem by x plus 5. Because remember, that's a 0. This is a 0 because if you plug it in here, that gives us negative 5 plus 5, which is 0. 0 times anything is 0. So that is the fully factored form. Let's check to make sure it reconciles with our first answer. Wait, oh no, this is just the test, right? This is just deriving the situation. So again, just pay attention to how the numbers are crunched. If you didn't know this, right? That's the whole idea. Like if you didn't know how to do this, here's the algorithm yet again. So you already know it's x plus 5. Because again, cubic root of x cubed is just x. Cubic root of positive 125 is just positive 5. So this part is very easy to get, but this part is the more annoying. So how do we generate this part using the algorithm? It's going to be, first you square that to get this one. We're going to multiply this times this one, including the sign, and we flip the sign. So x times 5 is positive 5x, but you flip it to make negative 5x. And then you square that one to get the last term, the constant. So, shortcut algorithm. It's again much faster. Well, not tremendously faster, but definitely more useful if you can apply it to something like this one. So that's the sum of two cubes. We've talked about the difference of two squares, the difference of two cubes, and now, just now, the sum of two cubes. Pretty nice algorithms, but they are kind of specialized. Okay, maybe several more problems. Let's do a mixture of situations. Starting easy, moving on to more moderate. So suppose we have something like 121 x power 4 minus 100 x power 8. So here's the situation. Don't forget your old stuff, of course. When you're factorizing such problems, always double check. The first thing you must ask yourself when doing generic factoring problems is, can I factor something from all the terms first? There are only two terms. So can we factor something from both terms first? This is just an 11 times 11. This is a 10 times a 10, so no common factors between those two. But this is x power 4 and this is x power 8. So there are in fact factors that are common with the x degree 8 and x degree 4. So make sure you factorize those ones first. So slap on the old parentheticals. This is a common factor and that one. So we're going to factor it out, bring it to the front. So thus, x power 4 times, this is gone, it's now just times 1. Coefficient remains unchanged. We factored out one of those, so only one of them is, the other one is left. So x power 4. Close parentheses. Alright. Now reevaluate. We have perfect square number 1, difference, perfect square number 2. So this is a difference of two squares. Straightforward factorization. Let's use the algorithm. Square root of that is 11. Square root of that is 10. Square root of that is x power 2. We're going to copy paste this one. Following the algorithm, so that must be the same thing. And this one must be the same thing, except the two signs have to be different. Minus, plus. Because again, you want if you distribute to get back to your original situation, this one must be equal size but opposite sign to that one. And we know 10 times 11 is the same as 11 times 10. And they both have x squareds. So this one produces a positive 10 times 11x squared. That one produces a negative 10 times 11x squared. So very deliberate. We know it's going to check out, and that's fully factored form for this scenario. So this one factorizes into that one. Not too bad. Let's do a sum of two cubes. So we're going to have something like, let's do, what's a good one? 24/3. Yes, 24/3. And then 24/3, we're going to have a to the power of 33, and then it's going to be minus 1. So what is this? This one, it's probably a perfect cube. This is definitely a perfect cube, because cubic root, you just divide by, you divide the exponents by 3, you get whole number exponents, so perfect cube. And 1 is a perfect cube, so probably a difference of two cubes. Follow the algorithm. What is the cubic root of the first term? We need to put it right here. Cubic root. Well, like I said, this one's easy to do. You just divide the exponent by 3. That's the cubic root. But this one is a little messier. So you just have to factorize it. If you don't know it, I wrote the problem, so I know it's just going to be 81 times 3, so I already know that. But what is this exactly? If you don't know that right off the head, you just need to do the factorization. So divide by 3. Nice. Then we know this is just 9 times 9, and we know that 9 is just 3 times 3. 3 times 3. Altogether, unfortunately, this is 3 to the power of 5. Well, that's not the best situation now, is it? That's okay. We can still do it. So we're supposed to take the cubic root of this one in order to produce this. So just apply the cubic root. So switching back into radical notation is going to be cubic root of 3 to the power of 5. Okay, this is just a review. How many 3's fit into the 5? Just 1. So we could pull out only 1 3, exponent 1. What's left over? Well, what's 5 losing 3? We have 2. So it's going to be cubic root of 3 squared. So that is the cubic root of that one. Does it look nice? No, but that's okay. Let me just clean it up a little bit. So it'll be cubic root of 3 squared. Again, not the nicest scenario, but it's fine. What's the cubic root of negative 1? It's just going to be negative 1. Easy. Now here comes the annoying part. Again, to do this one, you need to memorize the algorithm, or you need to just derive it. So this squared will take you to the first term. This is kind of funky though. When you square it, here's the little trick again. This is technically exponent 1. When you're squaring it, you're just multiplying 1. So if you translate this back into fractional exponent, think about squaring it. So all you're doing is you're just doing the 2 to the exponent 1, which is the exponent right there. So if you square that, it becomes, you could put it like this. This is technically true. You could also put it like this, which is also true. There aren't any negative shenanigans to worry about, so this is a safe move to do. And then you square that one, of course. So what is that? If we square the first term, we get this first term inside. Next, you take this one times this one, flip the sign, and you produce this. So constant times constant. That's pretty nice, right? It's just negative 1, so you just put a negative in front of here. So it becomes negative 3 cubic root of 9 a power 11. That's it. Lastly, you take this and you square it, and you get to this term. Pause 1. That's it. We are finished with the problem. I didn't intend for the coefficient to be that gross, so I'm sorry. That's the way it be sometimes. Alright. So that's the difference of two cubes. Again, make note of the signage right here. If this is a negative, then this is, oh, I forgot to change it. This is a positive. Remember I told you to, remember I said to flip the sign? I just forgot to do it. So again, this one times this one gets you a negative first. You flip it, it becomes positive. Just following the algorithm. So difference, 2 cubes. Again, sometimes the number ain't exactly a perfect cube or a perfect square. That's okay. So sum of 2 cubes. Now you know what? Let's move on to factor by grouping, because I am running out of time. I do have something to do in like 20 minutes. But then I'll be back on probably later, just to go over a bunch of random problems. A plethora of mixed problems for factorization. Alright. So factor by grouping is what it sounds like. Easier said than done, of course. It's easier to see the actual problem. So let me write a problem real quick. There's going to be 2x minus 1, and then you'll make note that I'm writing a y here plus 2. So this is a 2 by 2 expansion. It's, you know, just use the 4-letter F word to do this process. So first one times first one gives us 2xy, and then first one times second one gives us 4x, and then we're done with this distribution. Second term times first, and then second term times second. That's full distribution. Alright, so we've distributed this 2 by 2 successfully. So if you distribute a 2 by 2, we're supposed to get 4 terms. 1, 2, 3, 4. But there's nothing to combine, so our answer remains as 4 separate terms. In contrast, if you were to distribute something with just x's, I would just want you to make note of something. This is technically 2x times x. This is going to be minus x. That's going to be plus 4x. And that's going to be minus 2. So pay attention to the similarities between those. So this is basically the same as this one. It's just this one is combinable and that one is not. And then this one corresponds to that one, right? But no, I'm not gonna say but. So this one corresponds. Oh no, I kind of mixed up the order, didn't I? This one corresponds to that one. Yes. Yeah. There you go. So that's fine. And then this one corresponds to that one, right? Yes. And then lastly, this one corresponds to that one. Okay. So for this situation, it's quadratic. These ones happen to be the same types of terms, so they are therefore combinable to make positive 3x. But these two are not of the same types, so they cannot combine, so you leave them separate. So I'm pointing this out because I just want to draw your attention to the similarities. But this one, you cannot combine those two. Alright. So when we're doing factorization, thusly, we cannot use the same algorithm we typically use for a quadratic, because this is not a quadratic, because again, these two were not combinable. But here's a nice thing. This is something called factor by grouping. All you have to do is pay attention to the ones that look very similar, paying particular attention to the coefficients. So this coefficient, if you double it, gets you to this one. This technically -1 coefficient, if you double it, takes you to that one. That's a very sneaky suspicion. So here's how the factor by grouping works. You group those two using the old parentheticals, and then you group those two using the parentheticals. Now this is where you need to be a little careful, probably. This one's copy paste, no problem, because they're all positive signs. This is the sucky one. See how this is negative, this is negative? Well, some people like to put the negative out in the front in the beginning. I advise against that when you're starting out. So I'm going to keep the negatives inside here. So -y, -2. But if you put a plus, it is always true, because distributing positive signs doesn't change either of those two. But if you try to be fancy smancy and then you try to put like a negative here, and it's like a positive, some people goof up the signs. So again, my advice is to just take this one, enclose it within the parentheticals right away, and then always put a plus. You are always right. Alright. Now you just do basic factoring. There's two terms here. Pay attention to the similarities. There's a 2x here, and there's a 2x embedded inside there. It's just 2 times 2x. So from those two terms, we can factor out positive 2x. So see what happens. So factoring the 2x from those two, factoring out the 2x, we are going to produce a resulting, this one divided by 2x is gone, so just y, this one divided by 2x is just 2. And then this one right here, what's common to both of them? Well, there's a negative sign here and a negative sign there, so you can factor out a negative 1 from those two. Now let me just be complete. So it's technically plus, and then if you factor out the negative 1, the negative 1 goes out in the front. Like so. Once you divide by negative, it becomes positive. Sign flip. This one also sign flip. So there it is. Not coincidentally, if you pay attention, isn't this factor right here, this blue thing here, the exact same thing as this red thing right here? Because this is literally y plus 2, and that is y plus 2. So that's a particular setup. So if you think about it, this blobby thing here, we can call it p, and this blobby thing here is the same thing as y plus 2, so that's also a p. So I'm substituting it just to make it more explicit. This is 2x plus, or 2x times a p, plus a negative 1 times the p. So now you can do another factorization. You could slap on the parentheticals once more. And since this is term number 1, which has a times p, and this is term number 2, which has a times p, you can factor out the p outside of these new set of parentheticals, thus yielding p times parenthetical 2x plus negative 1. Now just change to minus 1. So that is conceptually what's going on, but p, you don't want to introduce more letters into your scenario. So p is just a visual way to condense this y plus 2. So p is just y plus 2. And then the rest of the stuff is just copy paste, copy paste, copy paste. Obviously, you don't want a different colored ink if you're like writing this down. As you see, it's going to match up with the beginning scenario if we distribute, which is right there. So this one should match perfectly with that one. That's how we generate the problem. So that's it. That is factoring by grouping. Telltale signs that you have a factoring by grouping problem. Like 90-ish%, 95% of the time, maybe 98% of the time, it's just going to be an even number of terms. So if you have like 6 terms, if you have 4 terms, if you have 8 terms, it's a very, very, very big clue that you can factor by grouping. Very basic setup. If it's not a trinomial, if you don't have a quadratic looking thing, and you have an even amount of terms, and you're supposed to factor, it's probably factor by grouping. Not guaranteed though. In particular, you want to pay attention to the coefficients as well, because you can see there's like a pattern of sorts. There's similarities if you decide to do certain types of grouping. But there are more ways to form groups. I'll show you real quick. So proceeding down this pathway is one type of grouping. We grouped the 2 terms that have x's and 2's together to make this first group, and then we group those leftovers to make the second group. But that's not the only way we can proceed. There are many ways. There are multiple ways to do the groupings. So we could just as easily group this y here, this y term with that y term. So I'll show you what happens. You can group in, you can add in any order you wish. So visually you can move this here, and then visually you can move that right there. So what's going to happen is you're going to get 2xy minus y, and then plus the 4x minus 2. Again, you can safely move things around as long as you keep the associated signs. And then technically, you're just adding in any order you wish. That's the commutative property. So here we go. And then now, this could be group number 1. And then the other one's going to be group number 2. Why are we grouping it in this way? Because we see that there's 2 here, and then there's a 1 here. Because this one is double of that one, and then this one is double of that one. Also, there's a y here, and there's a y there. So it makes sense to group those 2 together. So now let's factor common factor from those 2, the blue terms. So what's common to the blue terms? It's just going to be the y here and the y there. So factor out the y. What remains inside? So it's going to be 2x, because we divide this one out. And then negative y divided by y just gives us negative 1. There it is. What about that one? Same situation. You slap on the parentheticals. Remember, I would always recommend just putting a plus right away, because you're always correct if you put a positive. Always. What's common to factor term number 1 and term number 2? It is a factor of positive 2. So this one divided by 2 to bring it outside is 2x. This negative 2 divided by 2 is negative 1. Well, what do you know? That's the same thing, right? Again, that's not a coincidence. So I'm going to slap on one more set of, or rather set of brackets. And again, this is, now you got to take a step back. This is term number 1. It just looks funky. And this is term number 2. They both of those 2 terms has the 2x minus 1 there and there. So we can factor out this 2x minus 1 from both of these and bring it to the outside. Because again, conceptually, this is just one particular factor, purple factor, and this is technically purple factor. So since you have y times purple plus 2 times purple, you could just factor the purple out of the brackets. It's just that the purple factor has 2 terms inside it. But you treat it exactly like a factor. So take this factor out from those 2 terms and put it right there. So we're going to get 2x minus 1 brackets the leftover. What's the leftover? It's just the y here, because we divided this one to bring it out. So this part is gone. And then we have a plus 2. Again, we took this, we factored it out to put it outside the brackets. And then we successfully factorized it. Just make sure you clean it up. Make it look real nice. I'm going to change the bracket back to parentheticals, because it looks quote-unquote nicer. But as you see, this one matches what we had before and then the original problem. So that's factor by grouping. That's a pretty straightforward problem. Let me show you another one. Suppose we have something like a 3x squared minus x. No, minus. Let's do minus 2, for example. And it's going to be times. Let's do x power 1. And then let's do 2x power 1. And then we have a plus 4. No, plus 9. So this one, again, if you FOIL it out, I'm just going to speed run this one real quick. So it's going to be 6x cubed minus 4. You know, I like to do it in order. Let me do this one first. So that's going to be positive 27x squared, and then this one gets negative 4x, negative 18. So be flexible. Don't become stuck in the perpetual mindset of just foiling all the time. You can vary it. Okay, as you see, this is x power 3 type, this is x power 2 type, x power 1 type, and then x power 0 type, so nothing is combinable. So this is the problem you will be given, and this is technically the answer. So you're not supposed to see this one. So that's the one you're supposed to see only. So the question is, how do we do this? Well, you can actually jump straight to synthetic division if you really want to. It's not going to be tremendously difficult, because this is factors of 6, factors of 18. So not super, super bad if you're trying to do synthetic division. We're going to use that to check afterwards. But let's try to avoid that, because honestly, using synthetic division is typically a last resort, or the most generic resort. If you don't have special factorization rules, you resort to long division or synthetic division. But if you have shortcuts, because maybe you're going on a time test, then please use the shortcut. So we're not proceeding down the route of synthetic division, so let us first take a step back. So again, we have 4 terms. Can we factor something from all 4 of these terms? No. This is 2 times 3. There's no 2 here. There are no 3's there. So you cannot factor something from all 4 terms. But if you survey the x terms, you notice that this one is a x power 3, x power 2, x power 1, x power 0. So there are some similarities in the factors. So hypothetically, right? Hypothetically, if we group those 2 together, we can hypothetically factor out x squared from the 2 of those, like so. And maybe we could factor out those ones. So we need to check those factors of 6 and 27. So what are the common factors to 6 and 37? This is just 2 times 3. And that is just 9 times 3. So 3 is common to both of them. So 3x squared is common to both of those 2 terms. So let's do that. So if you slap on the parentheticals and then you factor out the 3x cubed, the 3x squared, we're going to get the 2 here and then the positive 2x technically, and then the positive 9 left over. So that's nice. But what about this one? Is that one also factorizable? Well, we have a negative here and a negative here. That's typically very nice clue. We have a coefficient of 4 and a coefficient of 8. Let's check the factors of those 2 real quick. This is a 2 times 2 x. And this is a 2 times a 9. So yes, there's commonality. There are common factors between those 2. And take a quick survey. You notice that this is a 2x plus 9. Isn't that a 2x and a 9? Is that a coincidence? Most certainly not. So slap on the old parentheses. You are always correct if you put a plus here. So now let's factorize from term number 1 and then term number 2 in the red parenthetical, considering also the negative sign. So we can factor out a negative 2 from the first term and a negative 2 from the second term. So factor out the negative 2. So this is now going to be gone, leaving us with 2x for the first one. Factor out the negative 2 from the second one, gives us positive 9. And make sure this one is the same as this one, which validates your decision to go down factoring by grouping. So because they're the same, we can continue on with factoring by grouping. So we can factor out the chunk of 2x plus 9 because it's also here. The chunk is 2x plus 9. So if you slap on the old brackets, we can factor out the chunks from both of those to the front. So it's going to be 2x plus 9 is the chunk we're factoring out. What's left over in the brackets? 3x squared and the negative 2. So that looks pretty clean. There you go. Can we factorize this some more? Well, depends. If your teacher wants rational coefficients, then this is the farthest you will go. But technically this is a difference of 2 squares. So if you really want to, you can go a little farther for this one. This is square number 1, that is square number 2. So let's follow the algorithm. Square root of this one is just going to be, well, not much to do with 3. That's just going to be irrational. So root 3 times x power 1 half exponent. And square root of 2 is just going to be square root of 2. Wonderful. Let's copy paste term number 1 here. And then term number 2 there. 2 signs are different. So I'll put a negative here and a positive here arbitrarily. So that is a fully factored form. However, it does have irrational coefficients. So depending on teacher, you might have to go forwards, or you could just simply stop right there. So fully factored form. Wonderful. So that's recognizing that you can do factoring by grouping. If you did not recognize the factor by grouping, well, you'd have to resort to synthetic division, right? So extract the coefficients first. We have 4 coefficients. This is exponent 3, exponent 2, 1, 0. So all terms are present, and we need to account for them. So 6, 27, -4, and then -18. So no invisible terms. Like I said, if you proceed down this synthetic division route, you have to consider factors of 18. 1, 18, 2, and 9, 3, and 6. Over candidates of 6. 1, 2, 3, and 6. Plus or minus. So this one requires a bit of guesswork. I'm going to cheat, though, because we have the answer here. So the 0 of this factor is going to be -9 over 2. So that is the 0. So that's what we're supposed to guess successfully here. But how many of those are what's the probability of guessing the one right off the bat? But let's see if it works. So this one, drop the 6, multiply. Right? Yeah. Summate, multiply. Summate, multiply. There's, boom, right there, 0. Perfect. What's that one? Those are the coefficients, remember? We started with cubic. We're dividing by positive x power 1 plus 9 halves. So this is going to be x squared. This is just x1, and this is constant. And is that what we want? Yes, technically, right? Because you could factor 2 from here and here. So that is the same as that one. And then the 2 here, you can just multiply to that particular factor, which is, again, technically x plus 9 over 2, because that makes 0. But you can take this 2 to beautify this factor to distribute. We're going to get 2x plus 9. Again, that's just to beautify it. And this one, copy-paste. And there you go. This one matches that one perfectly. So if you proceed down the synthetic division route, you have to do this first. You have to get lucky, are you favored by the RNG? If you're successful, then you can get the answer very quickly. But the probability of getting that, I don't know. I would probably test 1 over 1 first, or 2 over 1 first, which leads, to just guess and check at that point. Or you could just recognize, that this one is essentially a factoring by grouping situation because of the similarities of the coefficients, and then the fact that the exponents, there's a pattern to it. So minor clues here and there. But like I said, I gotta go. I'm gonna take care of a few things first. But I'll probably be back maybe later, in like 4 hours or so, to do some more of these problems. Or maybe I'll do a different subject altogether. Maybe back to English in regards to standardized testing, or maybe even biology. But that'll be it for now. So until next time, have a good one.